All right, we are now in session 5 for ML model eval metrics. This is categorical cross entropy. We're picking up where we left off last time in our session 5 lecture. We're going to go through session 5 and probably session 6 today, and then it's a short day today, so we'll end a little early. Categorical cross entropy. So the mean in this section, by the way, this is when we were talking about multi-class classification. We talked about multi-class metrics such as accuracy, confusion matrices. We talked about macro, micro, and weighted averages. How do you average the classification across n, or how do you sum the classification across n classes, sum and average? And now we're going to talk about categorical cross entropy and then one versus all and one versus rest strategies. Okay. Sorry, got to navigate. So categorical cross entropy, also known as the softmax cross entropy or multi-class log loss, is a function that's commonly used for multi-class classification, and it measures the difference between the true probability distribution of the target classes and the predicted probability distribution. So this metric works with distribution outcomes. I should put this in full screen. Here's the formula. So this is categorical cross entropy, and the formula is the sum across all of the classes. And we're taking the y true value at I times the log of y pred at I. So we're multiplying those two things together. So this is very similar to the formula the cross entropy formula that we were talking about. This is just a more generalized form. And then you got the negative sign in the beginning still to negate that, because your log's going to give you a negative value at the end of the day. So the log sign will negate that. So this is a more generalized formula than the one where we're looking at for basically just binary classification. This calculates that cross entropy for that. This calculates that log loss value for all of your classes. So categorical cross entropy. This is the formula you would use if you were doing a multi-class classification problem as opposed to a binary class classification problem. Hopefully that resonates with you guys. I told you guys we would use that formula a lot in this session, and we will see that quite a bit. So the categorical cross entropy calculates the loss for each instance by comparing the true probability distribution, which is a one hot encoded vector, with the predicted probability distribution output by the model. So you're essentially running your log loss function, but across all of the different classes. So you're running that n times across all the classes. Just like our typical binary log loss function, it penalizes for confidently incorrect predictions. So when the model says, hey, I'm really, really sure that it is of this class, and the probability is 0.9 or 0.8, that gets penalized really heavily if it's incorrect, as opposed to it saying, hey, with 0.6 or 0.55 probability that it belongs to a given class, that gets penalized to a much smaller degree. So confidently wrong predictions are penalized heavily. It's used very widely in training neural network models, as you guys might imagine, for our multi-class classification tasks. And it encourages the model to only output those high probabilities when it has maybe a higher degree likelihood. It's a very conservative metric to use for outputs. I have a video in here and we're going to watch it. I don't remember what it is, so. Can you guys on the StreamYard even hear the audio on my computer? I bet you can't. All right, nobody replied, so we're just gonna play this. So I told you guys that different people learn different modalities, and this is, here is, StatQuest is a good tool to explain. This is the interesting part. Okay, so in this formula, in this more generalized formula, the reason it's written so simplified is because we really only need to care about the predicted class, the actual class, the real class that it was supposed to be. So we're only taking the probability prediction as it compares to the actual outcome, because for the other outcomes, it will be 0. So that's why it's a simplified, which then you multiply by those and they go away. One more minute. All right, I think that was it. Hopefully that was maybe a little helpful, and if not, and the link's there. There's also some extra resources here for you guys if you want to continue uh, to explore more about that. But just like in our other cross entropy formula where it was sort of an on-off trigger, this one is an on-off trigger as well. It's just it's only on once, and that's for the class that you're trying to make the prediction for. So you're calculating the log of the output probability that goes through that softmax, and then multiplying it by that obviously -1 value, and then summing that across all of those observations, and then doing that across all the classes. Okay. There's one more thing to talk about when we discuss multi-class classification, and we touched on this a little bit, the difference between multi-class and multi-label, or one versus all and one versus rest. Or I'm sorry, one versus all or one versus one. One versus all is sometimes called one versus rest is all. So one versus all OVA, otherwise sometimes called one versus rest, is, sorry, scroll on my screen to be in the same spot, is when we train K-binary classifiers. So we have something that says, is it an airplane or is it literally anything else? Is it a truck or is it anything else? Is it a ship or is it anything else? So we have a problem where we are trying to classify documents, and this is a very relevant discussion point that came up when trying to design the model. I'll talk about that maybe more in a little bit. So one versus rest is, if you want to look at it kind of visually, how a model might see that clearly, there's 3 different classes, 3 different clusters here. There's green, blue, and red. We could say, is it green or is it anything else? Is it blue or is it anything else? And is it red or is it anything else? And this would be 3 different models, and or one network that has 3 binary classification, 3 softmax transformations on the end. One versus all sure there wasn't. One versus all is, oh, sorry, I'm starting to jump to the next one. So again, another visual of one versus all. We can construct 3 different classifiers, and each of those classifiers has its own decision boundary. So this is the decision boundary, that it's decided anything on this side of the blue of this line is blue for this classifier, and anything on this side is not blue. Anything on this side of the line is red for this classifier. Anything above that line is not red. Anything on this side of the line is green, and anything on this side is not green. What is one challenge that you guys can think of with this approach?
There's not that clean of a break.
What does that mean?
The points are close together for classification.
That's
no distinct grouping.
Yeah. No, that's a good point. I think that would be challenging in any classification, but absolutely, that would definitely be really hard to separate, and this may not be the best way to do that. What's one advantage? Well, let me describe the next approach first so you have something to compare it to, and then we'll talk advantages because I'm getting ahead of myself. I think it's on the very next slide. All right, I was jumping ahead of myself. This is what I was thinking of. Okay, so this other approach is 1 versus 1, where we train k times k minus 1, because if you have one thing to everything else, you don't need that last category, right? So if you have planes to ships, planes to trucks, and boats to trucks, you don't also need ships to plane, so they go both ways. So 1 versus 1, we can try and train k minus 1. So this just says, is it a plane or is it a ship? Is it a ship or is it a truck? Is it a boat or is it a truck here? So this is your really just very typical binary classification specific to 2 categories. You're asking it to decide separation between 2 categories. So 1 versus 1. I'm trying to think if I agree with this picture. Hold on. So the challenge here with 1 versus all is your decision boundaries here. You don't really know what this space in between these decision boundaries is supposed to be. Whereas 1 versus 1, when you're asking it, are you green or blue? Are you blue or red? Are you red or green? You have decision boundaries that meet each other. They come to meet each other. So this example that we're looking at up here, if you lined up all these lines together where these decision boundaries are, there potentially could be white space, right? Where we don't really have, it's other. What it is this is saying red or other, blue or other, green or other, and potentially if we lined up all of those lines together, you might get space that's just other, like broadly other. You're not red or green or blue. So the advantage of 1 versus 1 is you're forcing it to make a decision. You're saying you must choose. You can't be on the fence. So that's one example. Okay, multi-label. I'm going to get to this one thing and then I'll talk about the work example. Multi-label classification task is when we try to predict 0 or more classes for each input example. So in this case, you can either be mutually exclusive or you are not mutually exclusive. So we've touched on this before. I think I jumped ahead and talked about this in our open discussion class at one point. But there's multi-class and multi-label. So in multi-class, you're either a dog or you're a cat or you're a horse or you're a mouse. You cannot be multiple. You can't be a dog and a cat unless you're like a 90s TV show cartoon. And you can't be like a horse and a mouse, right? Okay, you got that one. So you have to be one or the other. Whereas multi-label, which this is a terrible example because you should have picked an example where you can be two things. We have documents at our work, and we're trying to predict the type of document it is. But on some pages, they can have two things in one document. The top part of the document can be Form A, and the bottom half of the document can be Form B. And so when we're trying to train a model, a discussion point that I proposed was, are we trying to predict, is this Form A or is this Form B? We should probably be leveraging, or at least trying multi-label classification, because one document can be both Form A and Form B at the same time. So our model detects the Form A-ness and the Form B-ness. How likely is it to have information of Form A, and how likely is it to have information of Form B? And those things can be true at the same time. Oh, I see this example. Sorry, the multi-label classification. It's asking, is there a dog in the picture? Is there a cat in the picture? And of course, there are some pictures where there is a dog. This is an image thing. There's a dog and a cat in the picture. You can tell I didn't look at my slides ahead of time because I missed speaking on them, so I apologize. That's what that picture is doing there. That makes more sense. So this would be multi-label. You can have more than one thing in a picture. Multi-class, picture, one thing. Okay, this is very grainy. So binary classification, you have to pick one. Multi-class classification, you still have to pick one of n. And these probabilities sum to 1. So you have a probability for label 1, you'll have a probability for label 2. You add them together, they sum to 1. Multi-class, these also sum to 1. So you have a probability for each label, even if you have 10,000 labels. And this becomes relevant in next word prediction for large language models. When they output like the probability of the next word, that's across all the words in the corpus. It's across, 10,000. And all of those probabilities sum to 1. So
you have to move your threshold like way down. Like what you just pick the most likely one?
Yes.
Okay.
Yeah, they just pick the most likely one, but I don't know, there's some other mechanisms in it too, because there's some clever stuff that they've done to make sure that the model just doesn't say the word the and get like stuck in a loop. So they don't always pick the most likely one. There's a little bit of randomness injected in there so that it doesn't get like stuck in iterative loops, but which was a problem they actually had initially in the beginning. So, but to answer your question, the reason I do say that is because sometimes people have this, as you're implementing AI for use cases, they have this assumption that, we'll only do it if the model has a log probability of 0.99. And well,
That's asking for a lot.
That's challenging when we're summing all of the probabilities across n classes and there's thousands of outcomes. So yes, you have to move your threshold, those expectations for those log probabilities down. This one does not sum to 1. This is also very important to know because it changes how this is output. So these are probabilities for label 1, label 2, label 3, and label 4 are independent probabilities. It's the probability of yes for label 1, the probability of yes for label 2, and they can both be 0.9. So they do not sum to 1. They're independent of each other. Okay, I guess I have a breakout. Let's see. Yes, I do. All right, let's go ahead and start this breakout. All right. So here we're going to implement one versus one and one versus all just to play around with it. You can load the iris data set, create a binary classifier just with our basic logistic regression classifier. Then try the one versus one approach and try one versus all approach. These strategies are available in sklearn using the one versus one classifier and the one versus rest classifier. So you don't have to write anything from scratch here. Let's spend 5 minutes on that. Let's come back at 7:01.
Why? Never mind. It's the same class number. It's still good to not one down.
What did you guys find?
They have really nice accuracies.
Yeah.
Like crazy nice.
Why are their accuracies so high?
It's simpler for it to understand. I don't. It's like me, you know, the biggest factor of accuracy is just giving you a big enough data set.
Does anybody have their code here they want to share?
I'm scared to show it.
So 4 lines.
It's about 3.5.
Let's look at why this accuracy is 1. Very important part of data science is when you feel suspicious, you should investigate. You should investigate.
That's everything from the equal sign.
Lesson for life: if it's too good, sounds too good to be true, it probably is. Oh, do I? Oh, yeah. Gotcha. No, I gotcha.
There we go.
Okay, so let's print this. All right, let's actually look at these predictions. Let's see what's going on here. Okay, and let's look at those compared to our true test, our true pd.data frame. Y test. Oops. All right, so it said it was a 1 and it was 1, said it was 0s, 2. Looks pretty good here. I actually don't see any situations where it got this wrong, but this is also a very, very small data set, right? Because we can see just by we have 30 records we're working with, which is not very big. And this is the accuracy score on our test set, which is the right way to do that. I don't think we can get any more data. No, we used everything we had. So it's just not a very big data set, but it does look to be getting the classes correct. Let's see what the, let's see this. And are we still getting?
Which means you get the big problem.
I want to see the difference between the accuracy.
Just
Yes. I bet. Well, we have an accuracy score of 1 just before we even do the 1 verse. So that didn't change that performance at all, which is interesting because I think here we have a slightly lower performance. Is that correct?
yeah, and like 9, 6.
Interesting. Okay, we'll have to look at this. That's very, very curious, very interesting. I have to delete all this stuff because I did this in the homework notebook. All right. Good, right? Okay. Oh, that was it for session 5. Let's pull up session 6. Okay, let's view. Go full screen and let me get it set up on my screen here. Maybe. So just, let me get out of full screen here. Maybe that's why it's not. Oh, I see. Okay. Okay. As part of model selection, model metrics, eval, we touched on this in the last class, and so we're just going to talk about it a little bit more. But part of selecting your best model has to do with hyperparameter selection and model tuning. So that was why in the last class, I think I had you put together a pipeline, or we talked about conceptually how to do it, but we didn't really talk about like what it is at a really detailed level. So we'll talk about k-fold, cross-validation, model selection, criteria, etc. Sometimes this is called experimentation. So when you run models, you design experiments, and you see which one performs the best through experimentation. You want to tune your parameters for your model. Often people use the terminology hyperparameters because they don't want the word parameters to be confused with the weights and biases. The weights and biases are also parameters of your model. Hyperparameters are what you select for your model. So which of these max depth parameters performs the best? How would we determine that? How would we determine which hyperparameter should we select for our model? Well, it's a little manual, in my opinion. And there are strategies and techniques you can employ to not have to brute force try every single solution. But at the heart of it, it's, well, let's train a tree with a max depth of 1. Let's train a tree with a max depth of 2. Let's train a tree with a max depth of 3. And and let's choose a performance metric. So this is where your performance metrics, everything that you guys have been learning, comes into utility. This is why it's very important to choose the right performance metric, because it influences which parameters you select as your best. Because perhaps if you had chosen accuracy, this max depth with the depth of 3 would have actually been the best tree. And so your performance metric that you choose by being the reward policy enforces your hyperparameter selection. So choose the right performance metric for your model evaluation. This is also why when you pass a metric to sklearn and its method that does cross-fold validation, hyperparameter selection, sorry, it will tell you, hey, I can give you outputs for all of these metrics. Yeah, I can give you accuracy, F1, whatever you want, but you have to choose one to be the metric that I use to select the model. And this is why. It will say, okay, which metric performed the best? And maybe in some situations accuracy performed the best, in other situations log loss. But what are you defining as like the winning metric? So if we define F1 as like the metric for which we select the best model, then of course the one here in the middle gets selected. Okay. That makes a lot of sense to you guys, everything we've been talking about, but just kind of bringing all those concepts together. So this is our process of optimizing our parameters. We want to optimize the parameters by selecting the right hyperparameters. And it's really to improve the model's performance. And what you're doing is you're selecting the model that gives you the highest metric outcome, whatever your metric outcome is. Hyperparameters are not directly learned from the data. So they are set prior to the training. Whereas your parameters, your model's learning that, it's updating the weights and biases through backpropagation, it's changing those, and it's learning from the data. You tell it what the hyperparameters are. You say, hey, max depth is 8 or max depth is 32. And then you evaluate the performance of the model after setting that value. So a hyperparameter is a value is a parameter whose value is set before the learning process, and they're not learned from the data. It's sort of a heuristic thing where it's not an exhaustive approach. Typically, you're not going to try every single value of a hyperparameter 1 to infinity. So it's sort of you're employing some type of like theory or strategy or search method to try to find the best parameter. Of course, constrained by time. You probably, depending on your data set, you probably can't train 1 million N estimators. So some of your boundaries will be defined by time and computational time and cost of training. Okay, so you guys know this, but in linear regression, coefficients are the weights and the intercepts. Those are the parameters, and hyperparameters are like learning rate. How quickly should we update the learning, or like how big of steps should we have? Should we have little tiny steps and we should just explore a little bit? Well, that's probably going to take us a long time to get there. Should we have giant steps? We might step over some minimas, some local minimas and some global minimas. So learning rate is something that you experiment with as a hyperparameter to see what is the best for your data and your problem. When the process of adjusting your hyperparameters or setting up cross-fold validation to try a bunch of different hyperparameters is called tuning. You're tuning your model. You're doing some model experimentation or some model tuning, and you're systematically searching through a defined set of hyperparameters, and you're finding the best one. So we have, a combination of parameters here: N layers, N neurons, learning rate, and then your model will do its weight optimization, and then it will produce a score. So you're training an entire model every time you change a hyperparameter. So it's very expensive is what I'm trying to say. And that's why we can't search everything. That's why we can't do everything. We have to use a little bit of common sense, our experience, our knowledge of the data, the parameters that typically have the most influence. We have to be a little choosy here because it's expensive, especially if you're working with like a really, really meaty data set or a meaty algorithm. So the process here, you're going to define, choose a search space, select a tuning method, evaluate the performance, select the best hyperparameters, and final model training. So I think that the piece I want to emphasize here is, I don't know if this is not the best visual for it. Let me see if I have it later. think we go through this, in very detail in K-fold cross-validation. But the point that I want to point out to you here is that we're going to do train test split, and on your training set, you're going to choose the search space, select a tuning method, and evaluate your performance. And this can be like an iterative thing. It should be a circle here. So you can do 1 through 4 and you kind of, repeat that loop. And you go through that a couple of times. Other people can do it. And then when you are set in stone and you find, yep, this is it. These are the parameters that we're deploying to production. You combine all of your data on whatever your best hyperparameters are. You combine your, of course you evaluate on your test set one time, as you guys know. That's your estimation for how this model is going to generalize in production. Then you combine all that data together. You take your test set, training set, everything, you squish it all together, and you retrain your model on those hyperparameters that you found were the best. So if you've done all of your model methodology, your generalization, then this should work out pretty well. Okay. I don't think we need to go through each of these. I'll just leave these here for you guys. Let's jump to search space. I feel like we've talked about this a little bit already. Did we talk about this last class?
Not last class, but I know in the first module we spent some time talking about hyperparameter tuning.
Okay, that's
I don't
helpful.
know how this will be like in terms of in-depth and stuff, but we did talk briefly about it.
I thought we did too. I might have a little look at my content and have a little overlapping content here. So the true search space is very, very complicated typically. And this is just, right now we're only visualizing 2 parameters, hyperparameters, because we're humans and anything above 2 is hard. But you can imagine that even as this expands to n, it gets even more complicated. So this is where we want to go. This is gradient ascent now instead of gradient descent, but we can't try everything. Look at how many things we'd have to try here and here and here and here and here and here and here. So trying everything isn't going to work for us unless you have a lot of time and a lot of money. And when we expand to multiple parameters too, this gets complicated as well, because in reality, we're just trying a bunch of spots, right? We're just picking a spot and trying it and seeing what the performance was. Maybe the dark colors are where it was good and the light colors are where it was bad. So we know this is what it actually looks like, not exactly these 2 things, but imagine this is what it looks like if we tried every single spot. But in reality, we're not trying every single spot. We're just picking things and trying them and seeing which one performs the best. So I just wanted you guys to be able to connect those graphs that you see of the search space and the potential parameter landscape to, in reality, we're not Google, Amazon, a thing. We don't have lots of money. We probably can't explore that entire space. So we're going to test and try different areas and pieces to the extent we can. Good. I did have this in here. This is what I started to say before, so I was getting ahead of myself. The challenge here, in addition to not being able to search the entire search space for hyperparameters, is something called the cursive dimensionality, which is that as we add more dimensions, it grows really, really, really large, and things become very sparse. That search space that we're looking at gets very, very sparse, and our points and values become very spread out from each other. So it expands massively. You can see that in a really simple example as we expand, one dimension, okay, things are kind of close together. And then we expand this into 2 dimensions and, things are getting a little more separated. And you expand to 3 dimensions and you can see how things really start to move apart from each other. There's just more space in between the points. So there's more space in between the points in 2 dimensions than there was in 1 dimension. There wasn't very much space here. And you can see that that's true of 3 as well. And so as we expand dimensions, as you expand parameters, you're expanding the space between those dimensions. So your search space just becomes huge. And it can get really, really complicated. That's all I'm saying. It's a challenge to find the parameters. And the parameters that we find are the best ones that we found from the experiments that we ran. It's heuristic, not exhaustive. But there are clever people that come up with ways of, searching this instead of just picking out. You can just pick things to utilize and based on your experience and research on the internet, or you can try some algorithms like random search or Bayesian search, for example, to try to help you select hyperparameters in a more efficient way so that the time you're spending searching for your hyperparameters is spent navigating the complexity and the vastness of that space in maybe a slightly more efficient way. So let's look at random, I think is the first example that I have here. So you could do a grid search. A lot of people do grid searches. Say let's do 0.1 and 0.001 and 0.0001. And so if you're going every 10th decile for learning rate, or if you're saying let's do 2, 4, 6, 8, something to that effect. If you see something that's laid out in very numerical pattern like that, that's very common. You'll see that quite a bit. And that's a grid layout. That's a grid search. It's actually probably not the best way to do a hyperparameter search. We like it. It feels nice as humans to think that the world is structured in data, and it's simple and it's straightforward. And honestly, I do it all the time as the first pass. However, our data really in reality is probably not structured linear like that. And so there's a lot of research that's been done to prove that random searches are actually better because there are going to be peaks and valleys and they're not consistent, So actually doing a random search puts values closer, further apart, and actually may result in a better outcome for you by randomizing the points that we're placing here instead of always placing them here and here and here because that's the values that we decided to try and test. So just something to take away, to think about, to read about perhaps. I think I have an article here that you guys can check out from Towards Data Science. We go until, when do we stop today? Do we go until 8? Yeah. We're going to keep going through the break, guys. And if we get done early, is that good with you guys? Okay. Because it's all going to be k-fold cross-validation. I think we'll go through this stuff pretty quick because we talked about this. Maybe I whiteboarded this or something. This is.
It was in the slide, first class.
It was in the slides. Okay. Well, I've got some overlap here.
Repetition is the mother of learning.
K-fold cross-validation is very important. So it is okay if we spend some extra time on this because you guys will use this. This isn't going anywhere. Even as we go into neural networks and evolve into that world, it may look and feel a little bit different. You may batch your data instead of cross-fold validation. So it's a little different. But it's not going away. So in k-fold cross-validation, we're going to split our data set into k equal sizes. We're going to do model training and evaluation, performance evaluation, then we're going to aggregate that performance in some way, and then we're going to assess the model performance. So if we have 30 instances, in K-fold validation, we split that into 3 different folds. And on the first fold, or on these, I guess I did it on the second and third. On the second and third fold, we're going to combine those 10 and 10 samples to be 20 samples. We're going to train and fit a model, and then we're going to make predictions. We're going to say model.predict on this third fold. We're going to do that each time for all of our folds. So repeat that, and maybe I should use a visual here instead of the words. Oh, look, I've got it here. There we go. So we're going to repeat that for each of the folds. So train, evaluate, combine these two and train, and then see how well our prediction versus our outcomes are on that third fold. Then we can take these different folds, fold 1, fold 2, and fold 3, and we can assess the performance. The performance when we trained on combined fold 2 and fold 3, the performance on fold 1 was 0.7. When we combined fold 1 and fold 3, the performance on fold 2 was 0.6. And when we combine these last 2 folds, fold 2 and fold 1, the performance on fold 3 was 0.8. So for each iteration, we can see the performance. And then we average the performance across. We take 0.7 plus 0.6 plus 0.8, and then we divide that by the number of iterations. We had 3 iterations. And we get the average here, which is 0.6. So the final performance of the model on our training set is 0.6. But all of you guys are expert data scientists, and you know that we don't just do train test split, but we do train validation test split. And so we also have a validation set sitting aside outside of that. And after we train our model, and let me see if I have a picture for this. Yeah, we also have to validate on the validation set. So after we train our model, here's putting together all of the validation, cross-validation test set. Here's our training set in the gray box. This is one iteration. Each row is an iteration. And each iteration has a performance associated with it. When we're done training the model, we get an output value, 0.6, which is the average performance across each iteration. That is our estimation for how our model will generalize. Out of that, we also have a set of hyperparameters. Perhaps here we can see that iteration 3 performed the best. So we assume that the hyperparameters we chose, I explained that wrong. No, forget what I just said. Assume we did this whole cross-validation thing. I should have one more picture. Assume we did this whole cross-validation thing 5 times across 5 different sets of hyperparameters. And this one performed the best at 0.6. The other ones were 0.5 and 0.55 and not great. Not below 0.5, because if it was, then we should just flip it, right? If it's binary. So we had this performance across 5 different things. This one performed the best. Great. Next thing to do is to take these hyperparameters, combine this data back together. So we have 30 samples, retrain the model with those hyperparameters over all of the data. And that is the output that we have. Our assumption is that model will perform at 0.6. And we run that model through our validation set, our 20 samples, and it says it's 0.5. Great. That's our assumption for how this type of model will perform compared to maybe a different type of model. Maybe you also ran a neural network. Maybe you also, have a rules-based engine or something that does a different technique, and you want to compare them all in the validation set, Great, we decided this one does the best. Now combine the validation set and the training set, all that data together, retrain it with those selected hyperparameters from our cross-validation exercise, then evaluate on the test set. Estimation is 0.5, combine all the data again. Great. Let's then retrain the model, and now we're ready to deploy it to production. We assume that the model performance is going to be how it performed on our test set, which is 0.5 when we put it into production. I hope this isn't accuracy, this performance 0.5. Maybe it's like, I don't know, something else. That's not very good. I should pause. Any questions on that? This is all stuff you guys know. Let me see if there are any trade-offs. Okay. In addition to just, I mentioned this, but K-fold validation, cross-validation is very expensive computationally. We're retraining the model every time. And based on everything I just said, you know that we're also going to have to retrain when we loop in that validation set, when we loop in the test set. It's just very expensive. So it's important to be conservative in your model selection parameters, and maybe even just as important to really get an estimation of how long it's going to take to run your model. So instead of this example here,
Just said, spurred a question.
Yes.
So when you're doing your model deployment, after you fit it on your train set, after you prove that's good against your test set, do you loop in your test set data and retrain on that?
Yes.
Okay.
Yes. You want to give your model as much data as possible. So you want to give it all the data possible when you're deploying to production. So you want to give it, like, it's like kids, you can give it the best chance to succeed in life. So you do. It's not going to hurt it to have more data. It's actually going to help it. And if you did all your techniques and it does generalize, that should be beneficial to the model. You don't reevaluate it though. So you add more data, retrain it, but your estimation for how that's going to perform, it's done. It's that test set that you had before.
Okay, cool.
That might be an opinionated thing, but I believe that's what you should do. Also, it's a thing that's lost on the internet. Like, I feel like people don't put as much emphasis on that on the internet as they should when they're giving how-to documents for how to do things. I don't think I have any slides on here about this, but I wanted to take a moment to talk about it as we're talking about K-fold cross-validation and runtime. So if you're trying to train your model over all these different hyperparameters, and you know it might take a long time, one thing to consider is trying to calculate an estimate for how long it's going to take your model to run. So if you guys are familiar with Big O notation in computer programming, Big O notation is like a way of standardizing the way we talk about code complexity in terms of runtime. So if you have a for loop, we have a data set of 100 examples, and you loop and do something over every single example. That's a big O of n, right? Somebody correct me if I'm wrong. But if you have a for loop within a for loop, so you say for every item in the list, for all of the categories that I have, do this thing with it. So you have 2 for loops now. So then you have a n within an n. So then you have like n squared, right? Something to that effect. Somebody called me out if I'm misspeaking, okay? So you have n squared. All of this is to say they have the same thing for algorithms. A random forest does not train at the same speed that a neural network does, that a linear regression does. So there are big O runtimes for your algorithms. And I have used those before and I found it very helpful. You can actually use those to try to like quantitatively say, it's not exact, but approximately how long is this going to take? And it's quite useful because I had a friend of mine, he was in grad school and he was doing his final thesis and he was training his final model, set up all the parameters, and it ran for like, I don't know, like a couple days. And he knew it was going to run for a while. And he's like, I should just see when this is going to be done. And so he like calculated the big O runtime with all the parameters, and it was going to finish well after he was supposed to give his dissertation. So you should calculate that so you have a good estimate. Can't just run models forever. It can get very expensive, and it adds up very quickly when you guys start having 3 parameters, hyperparameters that you're searching over, and you select 5 values for that. Suddenly you have like 125 models. So it can get very expensive. Big O notation for you can look up the mathematical complexity for the model that you're training. So sometimes some of these simple models, everybody, neural networks, woohoo, sometimes some of these simple models are very, very fast to train. And you can search over some space pretty quickly and get some utility out of that. Okay, pretty sure I already told you guys that, but in case I didn't, I have found it very useful. Model selection criteria. So generally speaking, okay, there's some things to talk about here. Generally speaking, we've talked about, most of the time you just want the model that performs the best, right? We use our performance metric, all the metrics that you guys have been learning in this class, as a way to select this is the best model because it has the highest accuracy, it has the highest precision and recall, it has the highest mean squared error, root mean squared error. However, there are other things that you can look at and are probably worth considering. And one is that computational complexity. How long does it take to train? How long does it take to run? How many, if you want to experiment with it, it's going to take you a very long time to rebuild that. What's the computational complexity is a real question. For a lot of industries and highly regulated industries, finance, banking, etc., interpretability can be very important. And there are certain laws and certain regulations emerging today that will not allow you to leverage algorithms that you cannot explain when you're making automated decisions. So if you are automatically approving XYZ from there, and it depends. The reason I'm being vague is because it's really specific to, it's state specific and it's use case specific. But if you're working with sensitive data and making sensitive decisions, it's worth understanding from a regulatory and compliance perspective, if you work in a highly regulated industry, whether or not you can even leverage those things. And just look at the companies who have leveraged those things and the ways they've been, penalized in the news and the class action lawsuits that come about. So even though some of these more complex models can be more predictive, maybe more powerful, there are still reasons to leverage these simple machine learning models, random forest, linear regression, logistic regression, where we can actually concretely explain. Because you can get down to, in linear and logistic regression, actual weights and biases, and you can say, well, we took 3 times this person's salary plus, 4 times the age of their credit, and that is why we made this, approval decision. So you can, that's what interpretability means. Why did the model make that prediction? And is it transparent enough for regulators to accept that as a reason for making a decision? That's a question worth considering when you are selecting your model to use, in addition to model computational complexity. Another thing that may not change your decision, or it may change your decision, but it's worth looking at, is the robustness of your model. And you can look at this through cross-validation. So if you have a large enough data set and you can make a cross-validation that's not just picking off too small samples in your data set, if your performance varies widely across your folds, if you're saying 0.9 and then on another fold you're seeing 0.6, you should ask yourself if that's really generalizing or not. I mean, that if you might expect to see that same type of extreme volatile variability when you implement it as well. So it would mean that your model across that run, for whatever reason, was not very robust. And that's something that's probably worth being aware of. Any questions on that so far? Oh, that was it. That was my last slide. We flew through that, guys. I thought I had breakouts for this, so let me see. I'm sure I do. Yes. Work on these breakouts, and then we will call it a day. I'm going to mute while I eat some chips. All right, we're having a great discussion. So we're actually going to continue to spend the time in discussion, but I'm going to end the stream so we can continue without recording.